Welcome, faithful followers. Welcome to the last part of the Redox section. If I were you, I'd go ahead and put me on pause now. I'd go get your favorite beverage, get yourself a snack. You might need it because this is going to be a marathon. I'm going to work my way through the rest of the questions. You'll see that we're starting at number 25, and we won't quit until we are through number 48. Mind you, there will be a lot of repetition. You're going to get really tired of dichromate and permanganate and malproportionation and disproportionation. If those things don't currently ring any bells with you, then it's a good thing you're here, and I'm glad you're here. So feel free to fast forward through me, feel free to skip around things, but what you can't do is just watch me work these. What you have to do is actually work these yourselves. So if that means if you need to pause and work one and pause and work one, that's probably not a bad idea to just go back and forth that way and work your way through them all. All right, so are we ready? Let's start right here with number 25. A solution of potassium iodide, well, you can bet that potassium's not going to be participating as a spectator, is added to an acidified, H plus will be involved, solution of potassium, yet again a spectator, dichromate. So a halogen in the ionic form, I minus, and dichromate are our two players. So our reduction half is going to involve that dichromate, which would be Cr2. 07 with a 2 minus overall charge, and that's going to always be reduced down to Cr3 plus. I call it the Aaron Brockovich reaction. If you haven't seen that movie, you should. Hopefully you get an edited version because it's got a little bit of language in it. But basically it was about a real story where there was a company that was polluting the drinking water of a town and telling them that the trivalent chromium with a 3 plus version was harmless, which was true, but that's not what was in the water. They said that's what they were putting in the water, but as a waste product. But it's the hexavalent, the +6 variety that we have over here in dichromate that is very carcinogenic, cancer causing, as you well know. All right, so there's my reduction half, and then my oxidation half is going to involve that I minus ion, and it's going to be reduced down to I2 with no charge on the molecule. You don't have to put the 0, I just do it for a habit. All right, so right off I need 2 of those. We know that to be true. And so what else do I need? Well, I see 7 O's on the left, so I need 7 waters to make that work. I'm having trouble writing a 2 today, aren't I? And then that means I have to force 14, count them, 14 H pluses over on this side. And so that makes a deficit of, let's see, 14 plus and a 2 minus makes a +12 versus a +6. So I need 6 more electrons to make that balance by charge. Then to do the oxidation half, I need 2 of those to start off. So now I have 2 negatives on the left, and I need 2 electrons to make that balance out. All right, so we're going to have to triple everything on the bottom. 6, 3, 6, the whole point of which was to cross off those 6 electrons. So we got that done. And there's not much else to clean up. So even though this looked all tedious, it really went pretty fast. So Cr2O7, 2 minus charge, plus 6 iodide, plus 14 whopping H pluses, goes to 2 Cr3 pluses, and 3 iodine molecules, and 7 lovely waters. And there you have it. If charge is balanced on each side, we can call this one done. Stick a fork in it. So we have +14 minus 6 leaves me +8 minus another 2 leaves me +6. So I got +6 total on that side if I used all my fingers and toes correctly. And 2 plus times a +3 is a +6, and the rest of it's neutral. So life is good. We are balanced by charge. Onward we march. Hydrogen peroxide. Yep, we see that a lot too. Don't forget about that peroxide ion, which is O2 with a 2 minus total charge. It loves to become water. It loves to become oxygen. But hydrogen peroxide is going to always decompose into water for you for sure. May or may not have the oxygen present. So hydrogen peroxide is added to a solution of iron 2 sulfate. So iron 2 can go up to iron 3 or down to iron metal. In this case, because we have peroxide present, which is going to be our reduction, because that O2 minus 2 ion is going to become 2 O minus 2s when we put it into water. So that's going to be my reduction half. So this time, this is going to be oxidized. So it's going to make Fe3+. Doesn't look like a 3. Really now it doesn't look like a 3. Okay. Here we go. Reduction. Hydrogen peroxide. You're going to see this a lot. Going to go to water. Well, once I do that, I'm going to need 2 of those. And now I need 2 more H pluses on this side. And that's where I'm going to get my 2 electrons added, because reduction is gain of electrons. So now they're neutral on both sides of that arrow, which is a good thing. And then my Fe2 plus is going to go to Fe3 plus. And what else? I think that's it on that one. All right, so what have I got to get going here? I need an electron, just an electron. So oxidation is loss of electrons. So they're following the definitions here. So we just need to double everything here so that we can cross off those electrons. That's the point of that. And now add it together. H2O2 plus 2Fe2 plus 2H plus. Got everything on the left. 2 lovely waters. And 2Fe3 plus. Total charge on the right plus 6. Total charge on the left. Plus 4, plus 2, plus 6. Life is good. Balanced on both sides. I'll leave that one up there a second. Sorry. All right, solid silver. Solid silver, so I don't have to think too much about that. Just write down Ag. Well, I'll wait a minute. Think Ag. Solid silver is added to a dilute nitric acid 6 molar solution. Okay, so this is the oxidizing acid. So our silver metal is going to go to silver ion. And when you have dilute nitric, if you look back at the lecture portion of all of this, you make NO gas. If you have concentrated nitric, you make NO2. So there's just some things you got to just give up and memorize and get over your own stubbornness. So let's do our reduction half and our oxidation half. Oxidation half is the easy one. The metal goes to the ion. You know that silver is a +1, so we just need 1 electron. So for reduction, we have H plus because this is a nitric acid. NO3 minus dissociates because it's completely, it's a strong one, so it dissociates completely is what I'm trying to spit out. And because it's dilute, I know I go to NO. Plus, I'm going to have to add some waters in here to get more oxygens on that side. Because if I start trying to balance, I'm going to mess up my ends. So I need at least 2 waters to get started, don't I? To get 2 more O's. So now I have 4 H's on the right and only 1 over here. So let's do this. And now I have 4 pluses and a minus. I have 3 plus, so I need to add 3 electrons. Total there. All right, so I've got to triple everything on the bottom and add these little devils together. 4H plus 3Ag plus NO3 minus yields NO plus 3Ag plus, oops, I didn't cross those off, plus 2H2O. Total charge on the left. Plus 3. Total charge on the right. Plus 3. Life is good. So sorry for coughing in your ear. All right, so if we keep going with this, we get good at it, don't we? Let's keep going. Now I have a solution of formic acid. Okay, confession time. I'm an inorganic chemist. But I will show you what formic acid really looks like. That COOH thing, that thing that looks so strange, is really C double bond O single bond OH that you may have learned about in geometry, biology, don't know where geometry came from. And carbon always makes 4 bonds, and so the only other thing that's connected to this carboxylic acid group, as this little puppy is called, the C double bond O single bond OH critter, is an H. So that's its structure, and that's why organic chemists write it that way to really keep reminding you it's C double bond O single bond OH as a functional group called a carboxylic acid group. And you can add all sorts of things onto that carbon, like long chains and such. This is the simplest organic acid possible, formic acid. So I'm going to write it, unfortunately, as an inorganic chemist would, because I'm too lazy to write all that out. It's HCOOH. I like it more as H2CO2, for a reason that will soon become apparent. So I'm going to have a reduction half, and an oxidation half. So I'm going to keep reading. So I got this acid, which I'm, like I say, going to write as H2CO2, is oxidized by an acidified, so we have some H+, solution of our good buddy potassium dichromate, or anybody else dichromate. Still got the dichromate thing going. So the dichromate, once again, is going to be reduced in the Aaron-Brockovich reaction. So from +6 down to +3. So that means I'm going to need 2 of those right off. I'm going to need 7 waters. Sounds familiar, huh? Which forces 14 lovely H pluses. And total charge on the left is +12. Total charge on the right is +6. So I need 6 electrons to reduce that charge down to a +6. Then my acid. I write it this way for a couple of reasons. Number one, I like it that way. Make no apologies for that. But number two is, what do these organic acids decompose into? Well, they decompose into your good buddy CO2. So you can see that just a little bit easier in writing it this way. So what else has to happen? I got my CO2. Oh, I need 2 H pluses on this side. Ooh, I got some H pluses to cancel out here in a minute. And I've got 0 charge on the left, +2 on the right. I need 2 electrons to make that little devil balance. So 6 electrons, 2 electrons, triple. Cross off, which was the whole point. Give myself a little more writing room. Not enough writing room. There, second time. All right, so now I can cross off 6 H pluses, leaving 8. And I end up with a grand finale of Cr2O72 minus plus 3H2CO2, or you can write 3HCOOH, your choice, plus 8 H pluses yields 2 Cr3 plus 3CO2 plus 7 H2O. Total charge on the right plus 6. Total charge on the left also plus 6, because the acid's neutral. I got a 2 minus on the dichromate, 8 hydrogens, plus 6 on each side. Oh, finally, an easy-greasy one. A piece of iron, solid iron, is added to a solution of iron 3. The only thing that metal iron and iron 3 can do in a redox situation, because this is just weird adding iron to iron, this being a spectator, is that we're going to have a malproportionation reaction, where we have FeO plus Fe3 plus going to Fe2 plus. This one is oxidized, this one is reduced. And that's what a malproportionation reaction is, where the same element is being involved in both the oxidation and reduction. And iron can do this, tin can do this. There's quite a few. Any of the metals that have double oxidation states can pretty much do this. All right, so it's not balanced, though, is it? No, that would be too easy. So, but it's a 2-3 trick. 3 plus on the left, 2 plus on the right. So I need 2 of these and 3 of these to balance by charge. And looky, looky, they also balanced by atom that way. So that's an easy, greasy one. Be on the lookout for them. Celebrate them. You'll know because you have taken the time to practice. An acidified solution of potassium permanganate, can see that a lot too, is added to a solution of sodium sulfite. So, permanganate is like dichromate, always reduced, because that's a +7 oxidation state on that manganese. So, it's acidified. We know we're going to end up adding some H+, but I'm just going to give myself some room here. What do we, in acidic solution, do with permanganate? Back in the lecture notes, it says it always goes to Mn2+. So there you have it. Now we have O's to contend with. 4 waters. We'll take care of that. 8 H pluses. And now we've got a plethora of charge on the left, +7 to be exact, but only +2 on the right. So I need 5 electrons, prime number involved. I feel multiply, multiply coming on. Oxidation half. SO3 2 minus. In acidic solution, it goes to your good buddy SO4 2 minus. Now, if you can't remember that, just think about it. If it's going to be oxidized, this is a +4 sulfur. This is going to have to be a +6 sulfur, so that's an oxidation. So either know that in acidic solution this is what happens, or just do the little simple, are you smarter than a 5th grader Jeff Foxworthy math. So I'm going to need a water over here on the left to get an extra O, and that introduced two H pluses, so I got some canceling of those to do in a minute as well. Total charge on the left is 2 minus. Total charge on the right is 0. See it? Minus 2 for the sulfate and plus 2 for the two H pluses. So I need 2 electrons. So I have a 2-5 trick. Dang it. Everything's got to go to 10 on those electrons. That's a pain in the butt. I should have said gluteus maximus. Okay, 5, 5, 5, 10, 10. 2, 16, 10, make that look more like 16, 2, 8. Gonna need more room. I have bad aim today, trouble writing today. Alright, so what have I got? I have 10 electrons. That was the whole point of all that multiplying business. Can I clean up H pluses? Yes, I can. I can get rid of 10 here, leaving 6 H pluses. Let's circle them so I don't miss them. What about waters? Get rid of all 5 and leave 3 waters. Circle those 2 so I don't miss them. So 2 MnO4 minus plus 5, count them 5, SO3 2 minus sulfide ions, plus everything's crossed off except 6 H pluses yields 2 Mn2 plus 5 SO4 2 minus, and everything's crossed off except for 3 waters. Total charge on the left, minus 2, 5 times 2 is 10, so that's minus 12, but take away 6, so that is a minus 6. So then I have plus 4, minus 10, so that's a minus 6. Yippee skippy, balanced. Okay, it's just going to be stubborn today. A solution of tin 2 chloride is added to a solution of iron 3 sulfate. Easy greasy. Metal ion, metal ion. Somebody's reduced, somebody's oxidized. A little bit of thinking, but celebrate the metal metal, because that is a spectator and that is a spectator. The chloride sometimes could be used to go to chlorine or to a chlor-8 or something like that, but not in this case. You've got metal metal. So what can tin 2 do? Tin 2 can either be oxidized to tin 4 plus, or it can be reduced to SN0. What can iron 3 do? Only reduction. So we're not going to do reduction. We're going to do that, because all this can do is become either Fe2 plus or FeO. How do you know which one? You don't. Be smart though, and pick one that makes this a little bit easier to actually balance. So think about it. Let's go with tin 2, SN2 plus Fe3 plus, going to the only thing that tin 2 can do, because it has to be oxidized, and that's the only way it can be oxidized. And then the only thing that iron 3 can do is either go to Fe2 plus or FeO. So it just got to figure out which one you want to do. So if I do FeO, let's see what happens. What's the total charge on the left? It's plus 5. Weird. What's the total charge on the right? It's plus 4. Dang it. All right, so if I do, let's work with the irons first. It doesn't matter. We got to work with somebody. You got to put a 2 in front of somebody. So I'm going to choose iron first and go 2 and 2. Okay, so what now do I have? Still a mess. So what if I do? That's plus 6, 7, 8, plus 4. What if I triple this and triple this? So I get plus 12 over here, because I had plus 6 here is what I was thinking. So if I make that plus 6, there we go, that works. All right, so you just have to be able to balance what you do. So it's just kind of a 2-3 trick to get to plus 12 on each side. You could also do it with the iron 2 plus, and it might have been an easier balance, but if you got it balanced, then you still get full credit. We actually give credit for a lot more than you see me do in these. There are more than one possible answer. I just usually go with the most common. All right, concentrated hydrochloric acid solution. Okay, so concentrated hydrochloric acid. so most likely the H plus and the Cl minus are going to participate in this, is added to solid. Yes, definitely. I'm going to have to dissociate that strong acid because I've got a solid to add it to. Solid manganese 4 oxide, and the reactants are heated. So we have H plus Cl minus plus MnO2. And MnO2 is sitting there with a +4 oxidation state on that manganese dioxide. So it's going to make Mn2 plus as it reduces, and we're going to make Cl2. So this is oxidized, and this is reduced. Now you can do this with half reaction if you want, but I think this one's fairly easy to do straightforward. I do need to add 2 waters. How come? Because I need 2 O's introduced, but that's not difficult because I can put a 4 right there. Oh, while I'm still in pink, I can also put a 2 right there. I think I'm done. What's the total charge on this side? +2 and +2. We're finished. So that one was actually an easy one, but you've got to know a few random acts of chemistry. And manganese 4 oxide is going to make Mn2 plus, just like you keep seeing permanganate do that. Those permanganate, or manganese rather, can make a lot of different oxidation states. All right, this one is the Iry-Rimson experiment. I have a strip of copper immersed, but this time it's in dilute nitric acid, and if it's dilute nitric acid, you make NO. Iry used concentrated nitric acid and made the brown choking NO2 gas. If you not have any idea what I'm talking about, I don't know how you got to this recording. Maybe your teacher just handed you a CD or a DVD or a thumb drive or some form of computer media with all these files on it. But if you go to the apchemistry.nimz.wikispaces.com page, you can see a delightful little video of a fabulous chemistry teacher elsewhere in the country, whose name I do not know, but wish I did, who did a great job of telling the Iry-Rimson story. Iry-Rimson is famous for inventing saccharin. CuO, that's a copper strip, because that implies a metal. In dilute nitric acid, but even if it's dilute, it's still mighty strong. And dissociates completely. So that's a no-brainer to get your reactants points. So again, you can go up to copper 1 or you can go to copper 2. It would go to 1 first and then 2, depending on concentrations, which we don't have any information about. Also, if you have H plus on the right, you're going to need to have some waters on the left. But I'm going to make NO gas. So let's deal with the waters now, because I need 2 of them to get 2 more O's. In which case, I now need 4 here. Total charge on the left is +3. Total charge on the right is only +1, but you know what? Since this is neutral, we can do that, and we'll get our charge balanced and not mess up anything else. So it's a good idea to get in the habit of saving this for last. When you have a single element that's participating, a metal or a halogen, shall we say. And there you have it. It's balanced. That's simple. Pressing forward. Our good buddy potassium permanganate is added to an acidic solution of hydrogen peroxide. Any AP biology students out there? Yes, you recognize this. This is the purple stuff in the burette. Yup, with catalase as a catalyst. So this is AP Biology Lab number 2. Who knew it was actually a redox titration? You didn't at the time, perhaps, but you will now if you go on to take AP Bio in the future. Or repeat it in college. They'll do that lab in college most likely as well. So MnO4 minus is my permanganate, and I'm going to have some H pluses, but also I'm going to have the H2O2 being oxidized. What will it be oxidized to? It's going to be oxidized to oxygen. That's the bubbles. And then Mn2 plus. Okay, so let's look on the reduction half first. I need 4 waters. And this looks familiar, doesn't it? 8 H pluses. What's the total charge on the left? +7. What's the total charge on the right? +2. So I need 5 electrons. Here comes 2-5 trick coming your way. H2O2 is going to make oxygen. Also makes water, but we already have water as a product in the top one, so I don't have to muddy the waters with doing that. Pun intended. So what else am I going to need? 2 H pluses. And 2 electrons to make it 0 on both sides. So there's my 2-5 trick yet again. So it's the difference between how peroxide decomposes in acidified medium versus basic medium. So I need 5 of everything on the bottom. So I can get to 10. So I can double everything on the top and get to 10 electrons, that is. And do some cleanup work. Scratch off, scratch off. That was the whole point. H pluses. I can get rid of all 10 of these, leaving 6 of these. And I like to circle them so I don't miss them. And I can get rid of, oops, that's not water. Can I undo just one stroke? Oh, look at that. Okay, so I've got to leave that like it is. So my big hairy mess at the end is 2 MnO4 minus ions plus 5 H2O2 molecules plus 6 H pluses yields 2 Mn2 plus 5 O2 plus 8 H2O. Total charge on the right is plus 4. Total charge on the left is minus 2 and a plus 6, also plus 4 total. Yippee skippy, balanced. Hang in there. We are on a roll. Solid copper is added to dilute nitric acid solution. We just did that. That was asked like wham wham, very close in succession in terms of the chronology of the test. So Cu plus NO3 minus plus H plus is going to yield Cu plus or 2 plus, whichever way you want to do it. But since it's dilute, we're going to make NO, and we got to have some water, so let's see how many we needed. When you have H plus, you know you're going to have water on the other side, but it also gets your O's that you need. So looking at copper, 1 on each side, NO, I got 2 on them, 2 on them. If I double this, I'm good. And that's going to make that have to be a 4. Okay, so what's the total charge on the left? Plus 3. Total charge on the right? Plus 1. Not to fear, because the plus 1 is coming from copper. So I can triple that to get plus 3. Did I do that right? And then I can triple this with no effect. So now what's the total charge on the right? Plus 3. What's the total charge on the left? Stays plus 3. Check. Check. We're good. Again, save that single metal for last. Now, here's a classic. We haven't run into it much, but here it is. Chlorine gas, so I know I can just write Cl2 for something, is bubbled into a cold solution of dilute sodium hydroxide. Okay, when you put a halogen of any sort into a base, a strong base, like sodium hydroxide or any other strong base, what you're going to get is a disproportionation reaction, where the Cl2 is going to both be oxidized and reduced. So go with the normal, it's going to make Cl minus, and then it's also going to make a version of a ClO. Stick with the lowest one and you're good. You can use any of them, but it's just going to be more of a balancing nightmare. And then because you have hydroxide on the left, you're always going to have water on the right. So anytime you put either H plus or hydroxide on one side, you're going to have some water on the other side, most likely, to make that all balance out. So I've got 2 O's on the right. I'm going to have to do that. And that gave me 2 H's on each side, so that's good. Ooh, and the charge even balances. Ooh, and the Cl's balance. We're done. So that's all I really had to do. But again, this is a disproportionation reaction where chlorine disproportionates. So we've seen in this set a malproportionation, where they kind of converge on the same. It was iron, I believe. And then now with a halogen, all of them can do this. So you learn it once, you get to use it a bunch of times. Here we go with permanganate again. Told you there were some things you're just going to get a little tired of. So let's go with this permanganate yet again. Solution of potassium permanganate mixed with an alkaline solution of sodium sulfite. So my sulfite is going to go to sulfate. My permanganate is going to go to Mn2+, make the rest work. Are there any Project Runway fans out there? Pretend I'm Tim Gunn going, make it work, people. MnO4 minus goes to Mn2+. You can probably do this one in your sleep now. This one, maybe not so much. We haven't practiced it as much, but there's my sulfite. It's going to go to sulfate. So that should get you started. So let's go back up to the top. I need 4 waters, which forces 8 H pluses, total charge on the left plus 7, total charge on the right plus 2, so 5 electrons. What about the sulfurs? I've got to get a water on this side. So why do I write 4? I don't know. 1 water will do it, and then I need 2 H pluses. And I've got -2 on the left, nothing on the right, so I need 2 electrons. Plus, Renault, every time I do this, I've stopped saying it because we are on number 37 for crying out loud. But remember what the definitions are. Rig, oil rig. Reduction is gain. See? Gain electrons. Oxidation is loss. See? Lose electrons. So I'm waiting that every time. I'm just not saying it every time. Okay, what else needs to happen? I just need to do the 5-2 trick and get the heck out of Dodge here. So double everything here. So I can get to 10 electrons. Quintuple everything here. So I can get to 10 electrons, so I can cross off 10 electrons and add this little mess together. I can also clean up some H pluses. Get rid of all 10, leaving 6. Get rid of all 5, leaving 3. So I need to get 2 MnO4 minus plus 5 SO3, 2 minus plus 6 H pluses, 2 Mn2 plus 5 SO4 2 minus plus 3 H2O. Total charge on the left. Ooh, okay. -2, -10, plus 6. What do you figure that comes out to be? -6? Yes, it does. -6. Plus 4, -10. -6. Check, check. Love it when that works out. I don't have to go back to the drawing board. Solid sodium dichromate. Don't have to think about it. My sodium ought to be in here. On the key, it's not. NaCr2O7. So I'm going to liberate a sodium ion over here on the end at some point. Might as well just get that out of there because it's going to dissolve in acid. So, solid sodium dichromate is added to an acidified solution of sodium iodide. Okay, that sodium is not going to participate, so I can just take my iodide. This is going to be my reduction. This is going to be my oxidation. And I can make I2. I'm also going to make Cr3 plus. Yep. So I don't really need that sodium in there. There's going to be so much there. That's why they left it out. So I can leave it out too. Let me clean this up. Cr3 plus. Okay, so what am I going to have? I2, because I'm just going to have sodium on both sides, and they're going to cancel anyway. All right, so I can get that out of here and put my charge. All right, so what have I got? I got to double this right off. I got to get my 7H2O and my 14 H pluses, which are tired of writing. Me too. And then I'm going to have my 6 electrons over here once I do the math again, plus 6 on the right, plus 12 on the left. And so I need plus 6 minuses to gain 6 electrons. And then my I minus, oh, sorry, I've written it over there. And I'm going to have to double that. And so I'm going to need 2 electrons, and I have to triple everything on the bottom now. So my 2 becomes a 6. I said triple, right? Yep. And that becomes a 6 because the whole point was to cross those off. Can't clean up anything else. Cr2O7 2 minus plus 6I minus plus 14 H pluses is going to yield 2 Cr3 pluses plus 3I2 plus 7 H2O. And again, these sodiums cancel off. Even though that says solid, they're not part of the redox process. They were both just going to stay Na+. If you left them in, that is fine. It's certainly not wrong. It just made your life a lot more tedious. All right, total charge on the left, -2, -6, plus 14 is a +6. Correct? Yes, it is. And then a +6. Check, check. We're out of there. Number 39. Hot hydrogen is passed over hot iron 3 oxide. Well, iron 3 oxide's rust. It's solid. Hydrogen is a gas, so the product side is pretty simple. H2 plus Fe2O3 solid. Well, all that's going to happen is a decomposition. But decompositions where elements are involved are redox. Yeah, we didn't tell you that back in first year chemistry, did we? Oh, no. We had pity on your soul. Yeah, we show no mercy now. All right, let's balance this. What do we got going on? I need 2 of these. O's are troublesome. I need 3. But I can fix that by putting a 3 there. And I think I got it. It's neutral on both sides, but I got to balance by atoms. So 6 H's, 6 H's, 3 O's, 3 O's, 2 Fe's, 2 Fe's. We're good. We're good. So think about who was oxidized and who was reduced. This was 0 to start with, and now it has become a +1, so this is oxidized. And it's this, the O's are -2 on both sides. That's not a player. This was Fe3 plus, and now it is Fe0, so this was reduced. So it's still a redox. It just looks a lot more like a single replacement reaction, which, again, a lot of reactions are redox in reality when you get down to it. You can hang in there. We're almost done. Okay, we've got 6 more to go, I think. 7, actually, because I'm just now doing number 40. Okay, let's go with solutions of potassium iodide and potassium iodate. Oh, this is an easy one. All right, this is a malproportionation. So the I- and the iodate ion both converge on I2. So my reduction is IO3-, because that I has a +5 oxidation state. Use all your fingers and toes. Yes, +5 oxidation state. And it's going to I2. But I'm going to have to double this to get 2 I's on each side. And so now I need 6 waters. So that's a passel of H pluses, 12, a dozen to be exact. Total charge on the left is +10. Total charge on the right is 0. So I need 10 electrons. Oxidation half is easier by far. So they both converge on I2. So I need 2 of those, and I need 2 electrons. See? Much easier. Makes up for the other one. So now come along and quintuple all of this. So that becomes 10. That becomes 5. That becomes 10 so that you can cross them off. There's nothing else to clean up. So I simply get 2 IO3- plus 12 H pluses plus 10 I minus. My antenna's going up a little bit, all even numbers. Man. 6 I2 and 6 H2O, still all even numbers, so I really need to reduce this to lowest terms, huh? Did I do it all correctly? What's my total charge on the left? 5, 6 minuses and 6 pluses is 0, and 0 on the right. There we have it. That one I'm going to actually box because it doesn't stand out as the answer. Okay, that's a malproportionation reaction. Hydrogen peroxide is added to an acidified solution of sodium bromide. So got to figure that as a spectator, but you got to also figure it's going to make bromine. So that's easy. So H2O2 is going to go to water. My oxidation half is bromide. It's going to go to bromine. All right, so back up at the top. What do I got to do? I got to double this, which is going to force me to add 2 H pluses, which is also going to force me to add 2 electrons based on charge, and reduction is gain, so that's a good thing. I need 2 of those, and 2 of those, and they cancel. Yay! So I get 2 Br minus plus hydrogen peroxide plus 2 H pluses yields bromine, and 2 H2O forms 2 liquids. Uh-oh. Sorry about that. Didn't mean to startle you that way. We're in the home stretch. All right, let's go with blue. Even though chlorine is a green gas. All right, Cl2 bubbled into a cold dilute solution of potassium hydroxide. All right, you have to just know this one. When you have a halogen in a strong base, it is a disproportionate reaction. So make the halide, and then make an oxyhalide. Stick with the one oxygen, and your life of balancing will be a lot easier. You can make others. It's not an illegal maneuver. But I'm going to be balanced here as soon as I make 2 O's on this side. So I have -2 on both sides, and I'm done. Otherwise, your O is going to get a lot messier if you start adding ClO2 minus, ClO3 minus, etc. So I didn't need all that room after all. So again, I say that's it's a dis. It's a disproportionation because Cl2 minus with its 0 oxidation state went to a -1, and it also went to a +2. Think about it. Oh, +3. So chlorine can have 0, -1. It can also have +1, +3, +5, +7. If you think about all the different ClO combos you know, that's the story on those. So it's a very versatile redox player. All right, this next one's a little goofy, I have to just say. A solution of iron 2 nitrate, okay, iron 2 is a candidate here, is exposed to air, oxygen, for an extended period of time. Well, we're going to rust. Don't you figure? We're going to make rust. But no, it can't be that easy. We can't just write iron 2 plus 3 O2s makes 2 Fe2O3s because we can't get that to balance. So we have to actually go through a reduction oxidation moment. Because my first inclination was simply go, ooh, rust. But you're never going to get that to balance. So we got to think about it a little differently. So my oxygen is going to go and make oxide. Easy enough. My Fe2 plus is going to go up to Fe3 plus. Then we can make rust. All right, because it's Fe2O3. Yeah, so I got to get the Fe up to a 3 plus. This one was goofy and borderline mean, I have to say. So how are we going to make this work? I've got to add, well, first I have to have a 2 there. Then I have to add 4 electrons. And then this one's easy. Just add an electron there. And so now let's quadruple everything here so that we can cross those off. And we get 4 Fe2 plus O2 yields 2 O2 minus and 4 Fe3 plus. Now, what's the total charge on the left? +8. What's the total charge on the right? -4 and +12 is +8. Check. Check. That one was goofy. Not a fan of that one. Wouldn't see that on the AP exam these days, I do not believe. But you might see number 45. I think I lied to you. I think we were going through 46. We're not going through 48. All right, a stream of chlorine gas. That looks like Cl2. Come on. Plus 2 OH minus. Well, here we are again. Halogen, strong base. Plus. And need some water. How much water do I need? I don't need that. That 2 appeared in the key, sorry. Let's try that again. That's what we're going to make. Now what? I've got an H on one side and not on the other, so I need a water. And now I've got 2 O's and 2 H's, so I need a 2 here. And I'm done. So it's disproportionation again. And then another fan favorite, look at that permanganate again. It's like, give it a rest. Do you feel like permanganate might be something you ought to know? Dichromate and permanganate? So a solution of 10,2 chloride, again, 10,2 could go or and go SN4 plus, or it can go to SN0. That's probably not going to do anything. Is an acidified solution of potassium permanganate. So you know this is going to be reduced. So you know this is not going to be reduced down to 0. It's got to be oxidized up to +4. Sometimes it feels like you're working a puzzle. So our good buddy MnO4 minus goes to Mn2 plus 4H2O, forces 8H plus, and total charge on the left is +7, on the right is +2. So our familiar 5 electrons. But let's make it look like an actual 5. There we go, 5 electrons. And then the easy part, Sn2 plus goes to, drumroll, Sn4 plus. Plus 2 electrons given off in that transition, and I got a 2-5 trick. 5, 5, 10, 10. Nothing to clean up. So 5 SN2 plus 2 permanganates plus 16 H pluses yields 2 Mn2 plus 5 SN4 plus 8 H2O. Did I get them all? Yes, 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 yes. Okay, total charge on the left, good grief, plus 10, minus 2, plus 16, isn't that 24? Plus 24. Good grief, Gertrude. All right, plus 4, plus 5 times 4 is 20, and a 0. Hey, 24. Glad to see you, 24, because that means we're done. Balanced. Now for the penultimate redox equation in the net ionic section. Any golf fans out there? That's the only place in sports I've ever heard the word penultimate used. It means next to last. All right, concentrated solution of hydrochloric acid, and for the love of God, potassium permanganate again. And it was added to solid potassium permanganate. But again, my potassium is not participating in this. So there is no point in dealing with that. It's the chloride that's going to take its place from the HCl minus. So when you see the concentrated solution of hydrochloric acid, you should be thinking H plus and Cl minus. And when you see the potassium, you know we're going to make potassium chloride, which is not going to be any fun, but we're also going to make chlorine gas. So the potassium still drops out of this. So we have MnO4 minus, yet again, being reduced to what? Mn2 plus, you say with resounding fury. And then the oxidation half is going to be my Cl minus going to Cl2. All right, so that one's easy. Just add a 2 here, so I need 2 electrons. It's that top one that's always troublesome, isn't it? All right, so I need 4 waters, 8 H pluses, 5 electrons. 2-5 trick again. 2, 16, 10, 2, 8. 10, 5, 10. Nothing to clean up. Try to use the word penultimate in a sentence today. Impress your parents with it. 2 MnO4 minus plus 10, count them 10 chlorides, plus 16 beautiful H pluses, yields 2 Mn2 pluses, 5 Cl2s, 8 H2O. Whew. Okay, so I've got minus 2, minus 10, plus 16. So isn't that plus 4? And on this side I got plus 4. Life is good. Check, check. Final. Should we have a drum roll? Drum roll. I know you can do better. a solution of potassium dichromate, I actually feel like no one's listening at this point anyway, I've lulled you into a coma, is in acidified solution of iron 2 chloride, spectator, dichromate, and iron 2. So you know that dichromate is going to be reduced, so that means that the iron 2 has to be oxidized. And there you have that. Okay, so let's deal with the dichromate. Cr2O72 minus. I know that was hard for you to memorize back in the day. It seems easy now, huh? Use it enough, it all gets easier. Cr3 plus, and we would obviously need, two of those. Plus 7H2O, and a whopping 14 lovely H pluses. And total charge on the right plus 6 total charge on the left. Plus 12, so I need 6 electrons. So I need to hextuple. Is that a word? Or just make that up? But the adding together part's easy. Cr2O7 2 minus plus 14 H plus 6 Fe2 plus. Got everything? Got everything? Yes, yes. 6 Fe3 plus 2 Cr3 plus 7 H2O. Total charge on the left. Minus 2 plus 14 plus 12 plus 24. Yes, yes. Plus 18 plus 6 plus 24. We're done. And when I say we're done, this time I really, really mean we're done. Stick a fork in us. We're done. So, God love you if you've made it all the way to the end of this. Your score will improve, no doubt about it. Don't forget that there are multiple choice points attached to this as well as question 4. Okay, I'm really glad you're here, and I'm really hoping that you have a great rest of your day. And I'm really glad to be through with this section, aren't you? Until next time.